My name is Kyle Smallgard. Obviously, you guys know what we're going to be talking about. A little bit of machine learning application, specifically targeted on showing you how to implement it on Android. As we go, if anybody has any questions at any time, feel free to just speak up. This is Minibar. If I'm not explaining something well enough, just ask. I can rephrase it. If I can't rephrase it, well, maybe we'll Google it or something. I don't know. So real quick about me, I've been programming on Android since 2011 about. I actually learned in this little room right here, kind of a piece of crap room. I had to wire my own Ethernet cord at one point because it broke. It was real fun and exciting, but we only have 45 minutes, so we'll skip that story. I currently work at SPS Commerce, is what my wife refers to as my big boy job, the one I go to on a daily basis, and then I work on a freelance basis for a company called Gigster, where I do contract Android development. So if you have any questions about either of those at the end, feel free. So what are the goals? What are we going to talk about? Basically, a basic understanding of some machine learning concepts, really only as it applies to this particular situation. We're not going to go too in-depth. My goal is to provide hey, this is the general concept, here's how we're going to apply it. I'm going to show you some equations, I'm going to show you some code, don't get too hung up on it. I'm going to do my best to keep it at a top level to give you an understanding of here is how easy it is to implement it. Hey, go learn the basics and you can do the same. And how we can do it on Android specifically. Not make you an expert, obviously. We only have 45 minutes, it takes longer than that. And not to provide you with a production-ready application. There's many problems with this application. The accuracy isn't super high. I took a lot of shortcuts to basically make it as simple as possible. But I'll cover some of the ways you could improve on something like this in the future. So, real quick, the first concept we're going to cover is supervised versus unsupervised learning. This is kind of the two general categories of machine learning. You've got your unsupervised learning, which is just a set of data points. You might know some dimensions about this data, but you don't know what the results are. For example, you know X, but you don't know Y. Or you know A, but you don't know B, and you're trying to find out B. And that's where you say, hey, machine learning algorithm, you go tell me what this data set is. As opposed to supervised learning, where you provide the algorithm with hey, this group on the left, these are X's, and here's all the information related to these pieces of data. And this group over here, these are all O's. Then you tell the machine learning algorithm, all right, now that you have the data, help me categorize new data. So that's kind of the overarching difference between supervised and unsupervised learning. We're going to be using supervised learning. It provides you with more accuracy, and there's a great data set out there that we'll be covering in a few minutes on what the actual data we used. So a few more concepts, classification versus regression. So with the first concept, classification, you've got a set of data, and you want to know, is this A or is this B? In machine learning language, that is this 0 or is this a 1? So you have a set of data on, for example, an x-axis. It could be any piece of data, time, dollars, size. And then you want to know, all right, is this a 0 or is this a 1 in terms of the problem set that you're trying to understand? Or you could have a regression type of data where you can have any point along this discrete line, you could have different values of y. Really very simple. It's 0, 1, or 0 to infinity. Or negatives, I guess. All right. Here's sort of the probability curve that you use for classification. Basically, I have does this show up? Yes, it does. Awesome. Oh, wait, I can make it a laser pointer. Nice. So you've got a probability curve which says as you go along the x-axis, what is the probability that this is a 0 or a 1? So way down when your x is closer to 0, however you define that, the probability value y is close to 0. As you move along the x, it gets slightly larger but not much until it hits an inflection point where it shoots up and says, all right, this is probably a 1. In machine learning, that's a 50% probability, or you can define it to whatever. You can move this curve to say, all right, well, 80% of my data is to the right, or 80% is to the left. You can move this curve however you want. But basically, you define that inflection point that says, at this instance, this defines my border between whether it's an A category or a B category. Man, come on in. Probably got some folks lost. Come on in, folks. There's one chair left, too. All right. Or regression, as we already discussed, we've got any point along the y-axis given your x values. And real quick, this is not simply a two-dimensional data. Two-dimensional, obviously, we've got a flat plane here. It's the easiest way to diagram something for humans to understand. But your dimensions can be anywhere from 1 to a couple 100,000 if you want. The more dimensions you have, obviously, the more accurate your data can be, or the more inaccurate if you're choosing bad dimensions. But for human terms, visualization is key, and we can only do 2D or 3D. So, which is unfortunate. All right, logistics regression. This is the basic concept that we're going to use for our classifier. And what this is, you have a set of data that we want to fit a line to, basically. If you remember from, what would that be, high school algebra? Probably. You've got y equals ax plus b. You've got your b, which is your intercept, and your a, which is your little, I forgot the name. Slope. Thank you. I don't have any notes out. So see, everybody remembers their high school algebra. It's finally coming to use. So this is literally the equation that we are going to use to demo the concepts of a logistics regression algorithm. It really is that simple, and you'll kind of see a lot of parallels. But we're going to define it slightly differently because we can. We're going to use the term theta, the Greek letter theta, capital Theta. And again, if you notice, it is very, very similar. We changed the order, and we're calling it theta 0 and theta 1. The reason we do this is because we're going to run out of letters if you use A, B, C, D, E, F, G for each of your slope terms, if you have more dimensions. When we use theta and a subscript, we can have as many as we want, and it looks cool. So, and I apologize for it looks kind of crappy, but I zoomed in on some of the equations. So, all right, so what are we going to do? To start out, we're going to pick random values for theta. And then we're going to evaluate y to see how our random values accurately interpreted that data. Were they close? Were they not? And then we're going to adjust theta to say, all right, you can move. We're going to increase theta 0. We're going to decrease theta 1. And it's going to be slightly more accurate. And then we're going to repeat just over and over again. And that machine is going to go through these iterations over and over again. And gradually, theta is going to get closer and closer to perfect. And then you've got your algorithm that you can implement. So what does this look like? So we've got our equation, again, written out with theta. We're going to pick random values for theta. Typically, with logistics regression, you start out with 0. Why? Because that's easy. There we go. We're going to evaluate y using this equation. This looks kind of complex, but if you recall back from your high school algebra, literally all we're going to do is we're going to measure the distance from our line, which is here. This is our zeros line, obviously. If you've got an intercept term of 0 and a slope of 0, it is simply following the x-axis. So what we've got, we're going to resolve our equation of h of x in terms of theta. So if thetas are 0, when x is any value, theta is always going to be 0. All right? So this term right here is always going to be 0 for our first iteration. Then we're going to subtract our y value, which is simply the distance from your x-axis to here. You're going to square it to get rid of the negative, and then you're going to sum over everything and divide by the sum divided by 2. It is literally, you're adding up the difference between your line and your points. That's all you're doing to provide, all right, how inaccurate or accurate is my equation. So you can see if your line was like this more, and I don't have a diagram, your values, the offset of y from your slope or from your line is going to be smaller, and smaller numbers are better. It's going to say my equation is closer. But we're going to update theta using this equation, which, if you know calculus, is simply the derivative. And I'm not going to prove that to you. Just trust me, it is the derivative of this equation. So, sorry, the whole thing is not. This piece right here is the derivative of this right here. And if you know the derivative is just how much does this line change from point to point. Really simple in this equation. It's literally just the slope pretty much. And then what we've got here is this alpha term. This is our learning variable. So looking at this equation, this is our update theta of j is what we're calling it. So we take our original theta, and we're going to subtract alpha times this derivative term. So alpha is typically a number around 0.1, 0.01, anywhere in there. It is really, there's a lot of different ways you can define it, or you can pick it. But in reality, it's just saying how quickly should my algorithm learn. The closer it is to 1, the higher your theta is going to change, because this value is going to be large. You got to be careful, because if you do that, your algorithm might overshoot and start bouncing back and forth. But if it's small, if it's too small, your algorithm is going to update very slowly, and it's going to take a really long time to converge to the value that you want. In all honesty, you're going to just pick a value around 0.1, 0.01, or try different values and just see how it turns out. There's various algorithms out there that'll pick a learning rate for you, but it's not really that important. If it doesn't work out, you usually just pick another and run it. So we already kind of covered that. With this point, yeah, I missed that. All right. So classification. We've got our classification curve. We call this a sigmoid curve. It's just a probability curve. We're going to define this as 1 over e plus z. And that's literally creating this curve right here. Because we want a 0 to 1, we want it bordered so we can go with 100% probability, 0 to 1. With our z is going to be defined as the exact same logistics regression equation that we used earlier. So what does this give us? This gives us our original curve if we had a straight line, and it's going to convert it into a sigmoid function. It says here's the probability that this point lies, or where this point lies on the curve. So if I've got an x value of, say, this could be literally anything. If my x's are defined from 0 to 100, and I've got an x value of 75, it's going to say the probability is about 95% that this is a 1 versus a 0. So how do we do it with multi-classification? If you're only going to have a 0 or a 1, how do you do multiple classification? Real simply, you make multiple algorithms and you just run it each time. So if you're looking for, is this result A, is this result B, or is this result C? You're going to create 3 separate algorithms, each tuned to different results. And then you're running the same data through it. So if you run the piece of data through your first algorithm, you say, all right, well, its probability is, I don't know, maybe it's probably a 0. With B, it's still probably a 0. And then you run it through your algorithm C and says, all right, this is pretty close to a C. So if your categories are all completely separate, after you run your data through here, you're going to assume that this is probably category C, because that's the highest probability out of each of your algorithms. And that's what we're going to do with our number classifier. We're going to have 10 different algorithms from 0 to 9, and we're going to run a digit through each of those algorithms and say, is this a 1? Well, there's maybe a 20% possibility. Is this a 2? 80%. Is this a 3? 10%, and so on. We're going to assume it's probably a 2 because there's an 80% probability. All right, how are we going to do this in terms of doing the algorithm? So we're going to use a program called GNU Octave. It's a free open source software that is basically, it's really easy to pick up and learn how to do matrix multiplication and implement some machine learning algorithms. There's a website, and all these slides and the Android code and the algorithm code are all up on GitHub. I'll show you guys the link to that at the end. So don't worry about writing down these links. We're going to use the MNIST data set. It's a set of, I don't even remember how many thousands of images, 60,000 images, I think, of handwritten digits from 0 to 9 that are all pre-labeled for our training set data. Because why not use it if it's already out there? Again, there's the link, which the website doesn't work a lot of times, but there's other mirrors you can get to. And then some GitHub code that'll help us out with loading this that I found. So, because again, why rewrite something when you don't have to? So what is our process going to be in Octave? And I'll show you guys the code as well. We're going to load and pre-process that data set. We're going to do a couple things to it that make it simpler, and I'll show you what exactly that looks like. But for every label from 0 to 9, we're going to initialize that theta again. We're going to initialize it to zeros. We're going to set up our cost function. That's the one that tells you how accurate is this line. We're going to run an inbuilt octave function called fminunc. All it does is basically it simplifies the iteration code and says that update function where we said you're going to update theta, it does all that for you. So it's just a simplification. And then we're going to export theta as a CSV. Why? Because we're going to import that CSV into Android to use it. Theta is going to be a 10 by 785 matrix. Why is that? 10, because we've got 10 algorithms we're going to use. 785, because we're using the MNIST data set is a 28 by 28 matrix, essentially, of data points for each number set. So 28 by 28 is 784. And with machine learning implications, you always add a bias unit. So we just add a separate, an additional item on there, which gives us 785. And I hit that. And this will make a little more sense once you see the diagram on the next page. So this is the MNIST data set. This is one piece of data. You can see, and this is a subset, columns 1 through 17. Obviously, there's 28 of them. You can see for each point, so this right here corresponds to this box right here. You can see we've got down to 28 and 28 across. For each box, it's a 0, obviously, if there's no data. And then it's up to a percentage, up to 1 for a density value. And in this instance, it's a 7. So you can clearly see this is a 7 on the graphic. Kind of an angled 7, but who knows. So one of the things we're going to do to pre-process it to make it simpler on Android, it makes the code simpler, is we're going to round every value up to 1 and assume that this is either a 0 or a 1. Makes it a little more inaccurate, but it also makes the code, if I'm looking at it at a beginner standpoint, way easier and way faster to run. So, and more intuitive, actually. All right, so how are we going to implement this on Android? Actually, you know what? Let's go walk through the code. All right. You know what? This is going to, yeah, there we go. Okay. So what we've got here is we're defining a training set and our training labels, and then a test set and a test label. We use separate test data from our trained data in order to accurately identify how accurate our algorithm is based on data that has not seen before. If you test on your training data, it's not going to give you a valid number, because you're going to say, hey, I've trained you on whether this is a 1, now you tell me if it's a 1. Doesn't really make a lot of sense. You're going to give it new data that it hasn't seen before in order to evaluate how good that algorithm is at identifying pieces of data it has never seen before. We're pre-identifying the number of labels we've got because it makes the code simpler. This code right here just displays that 7. Don't need to worry about it. We've got a couple of variables we're defining. Again, you can ignore all that stuff. Here's where it gets into the good stuff. We're going to define our theta as a bunch of zeros with 10 columns, as we said. We've got, 10 rows, because we're doing 10 algorithms. And then n, which is the size of our matrix, 784 plus 1. Then we're going to iterate from 1 through 10. We're going to initialize our theta to zeros, and then we're going to run, there's actually 2 functions in the demo code that basically do the same thing. But this is that fminunc equation where we use our cost function, I'll show you, and run it based on our preset parameters of, we're going to use a gradient object, and we're going to just run it 100 times. After we run it through that, we're going to determine what our accuracy is versus our training set, and our accuracy versus our test set. I'm not going to actually run this. It is pretty quick, but we don't have a lot of time. So I will show you what our cost function looks like. A couple notes in here, but you can see, well, it's not really helpful to see, is it? I wasn't actually planning on showing this, but then I just randomly decided to show you it. So yeah, not really important. We'll move on. All right, so how are we going to implement this on Android? Well, one, we're going to use some open source software because, again, I'm lazy, and if it's out there, I don't want to code it. We're going to use a library called Ink that basically allows you to draw on Android. We're going to use the efficient Java matrix library to do our matrix multiplication. So you might ask, why don't we just use a bunch of for loops versus matrix multiplication? The bottom line is matrix multiplication is a lot faster if you're using it correctly. And by using an open source library, you can then assume, yeah, it's probably using the faster implementations. So there's a link to that. It's quite a good library. There's a lot into it. Obviously not designed for Android, but it works. What's our process going to be? We're going to set up our Ink view. We're going to capture our input. We're going to break it into 784 bitmaps. Then, in order to make it faster, we're just going to analyze those mini bitmap borders, because we can assume that if our finger breaks the barrier of that bitmap, then that bitmap is now a 1 because it has data inside of it. So you could analyze every single mini bitmap, but then you have 784 times 784, well, 784 times your pixel density, actually, amount of pixels that you're analyzing every time, and it can take, if you do it straight up, it takes about 2 seconds on a Google Pixel to run, and that's very, very slow. So we make a couple assumptions by just doing the borders. But there's other ways you can do it if you want, and we'll talk about a few of those. We're going to run that result through our theta matrix. So our theta matrix has 785 terms to it. So if you think of our y equals ax plus b, it is y equals ax plus b plus cx plus dx plus, and each one of those goes on and goes on. So quite a big long equation, but we're going to run it through it, and it's actually really quick. And just like we talked about with our multi-classification, we're going to accept the highest percentage as the result, which may or may not be accurate. So we'll come back to the improving accuracy piece later. So what does this look like in code? Is that big enough? Hopefully. All right. So the code's actually really simple. If you use butter knife like I do, it becomes even simpler. So we are going to use our Gradle to import Ink, butter knife, and this EJML, which is that efficient Java matrix library. We're going to initialize our Ink view with a color of black because, again, we're using white or black as our definition. And we're going to set a stroke width. If you notice from that data set, the numbers were kind of wide, so we got to use wide numbers. The best accuracy is going to come out by modeling our data. So if you looked at, and this is something that we'll cover that I'll show you, but if you look at, for example, this 7 is written a little differently than some other 7s are written. So depending on your input data, your output data might not be accurate. So if I write a 7 like I write it, it might not necessarily identify it if all of the input data looks like this 7, if my 7 is more like that. So we make it wider. And then we just got a couple of buttons that are going to say, hey, calculate this or clear this value. The real key is after we click the button, we're going to get our bitmap. So we're going to say, hey, clicked our bitmap and split it into a 28 by 28. Wrote a little bitmap helper that takes in, all right, this is our Ink view right here, and we're going to split it into how many rows, how many columns. In this instance, we're going to split it into 28 by 28. And for each one, we're going to say, hey, does this border pixel, is it black or not? If it's black, we're going to break and say this bitmap contains black. And then we're going to move on to the next one. Our analyzer, let's go. So when we create our analyzer, we're going to open our theta output, which looks like, where'd it go?
So Kyle,
yeah.
When you said you're breaking the border, you're talking about that more coarse-grained grid that you're creating out of
Yes.
the board,
Yes.
pixels.
Yes. And I was going to actually diagram it out, and I forgot. But yes, if you think about it, let's see if we go to, so basically this is exactly what our Ink view is going to be. It's just going to be a canvas, and then we're going to split it up into 28 columns and 28 rows and analyze each of those little boxes to say, is this white or is this black? Yep. And we're doing that because that's exactly what our input data was used. So if our input data was a 36 by 36 matrix, well, then we would want to use a 36 by 36 in Android. So it all depends on what you trained your algorithm on. And this is what it looks like. You can see we're going to have a 10 by 785 and a bunch of random values. So what are these values? These are the weights. So these are theta 1, theta 0 for every algorithm. And you can see there's a lot of really random values. What they are, it's not really important, but this is what our machine learning algorithm determined that these weights should be in order to provide us with the greatest amount of accuracy. So how does this work? We're going to read in our, whoops, that's not what I wanted. We're going to read in our theta output file, and we're going to create a matrix of 10 by, in this instance, it's 785. And we're going to create a matrix using our matrix utils, which is from the efficient Java matrix library. When we want to analyze, we're going to take our input of 28 by 28 bitmaps. We're going to create a couple of arrays, and we're going to convert those. And in this instance, we're just checking the borders, again, to see if that contains black or not. We're going to create a vector. So this is where we're going to create a 785 by 1. So for each sub bitmap, is this a 0 or a 1? Does this contain black or not? For each of our points on our ink view. And then it's going to do a little bit of matrix multiplication that multiplies them together, runs them through a sigmoid function, and comes out with, hey, what's the maximum probability? Sorry, did you have a question? Oh, okay. So what does this look like? Not what I wanted. All right. So again, this is a really basic, obviously quite ugly app. Don't worry about it. I was never an interior designer. I remember, so when I was in 8th grade, I was doing, we made these little cars in industrial tech class. My teacher told me I'd never be an interior designer based on the color that I made my car. It was pretty ugly. But anyways, all right, so we've got our ink view. You can see we can draw whatever we want, and we're going to clear it out. So we're going to draw just a 1, because that's probably the most accurate. And boom, we can see it came out with a 1. If we look at, oh, come on. All right, so what we did here, this is an output of our 28 by 28 bitmap. So you can see there's 28 digits here, and then there's 28 lines. So you can see for the top rows, obviously that if I pull up my visor, you can see along these top rows there's no black. And you can see on this top row everything's a 0, which is exactly to be expected. As you go down farther, you start seeing some X's, and those are the values of those black boxes. And you can see it pretty much looks like a 1. And we're just going to feed these 0s and 1s into our theta algorithm, and it dumps it out. And you know what? This doesn't, here it is. Here's our probability matrix. So it says for this, so let me clarify something real quick. So the MNIST database goes from 0 to 9, but obviously in Android you've got a 0 indexes, could be 1. So in this instance, our first point, which is an index of 0, is actually our 1 value. So you can see there's a 99.9% probability that this was a 1. A very, very low probability that it was a 2. The 3 slightly higher, 4 pretty low. You can see the 1 is pretty straightforward. There's not a whole lot of disparity in what the 1 is. Some of the other digits, though, are a little less accurate. Let's try a 2. Sorry, forgot. So we did a 2, and it came out with this is a 2. Let's look at what it looks like. So you can see, again, we've got our 2 right here in black boxes. And our probability matrix, which is right here, says that this is probably not a 1. But hey, there's a 52% probability, which is not that high, that this is a 2. However, the key is that this is a multi-classifier. So if you look at all the other probabilities, they were all lower than that. So the odds are, actually this one's pretty high. Was that an 8? 7? Yeah, I could see that. So, but the key is the 2 is a higher probability than the other one. And how many people use Google Photos in here? Yeah, lots. So they run it through a ton of different algorithms to say, hey, what is the probability that this is a car? What is the probability that there's a tree in here? And they come up with those probabilities. If you ever actually look at, they've got an API out there where you can actually submit photos and get a probability matrix back that this includes certain things. And when it gives it back to you, it gives you back a value like this is a donut and a probability that says, hey, there's a 90% probability that this is a donut. And you can see that they're using the exact same multi-classification to define what is in each of these pictures. Of course, they're doing a lot more than 10 algorithms. They're probably running it through a couple thousand to determine what's in there. So let's see what else we got. Let's try, what number should I try? 7.
Can you do a 7 with a dash in the middle, like the European style?
Ooh, I don't know what that's going to do.
Can't see it.
Ah, damn. It worked. I promise it worked.
Does this recognition sort of like fail if you happen to be like off center with where you're drawing it? Like if you drew a 1 off
Yep.
to the side.
So here's one of, yes, we can try it, but I can pretty much guarantee it'll break. Yeah. So, and why this happens, if you think back to what was our data set? Our data set was 60,000 numbers that were all centered in a very specific size. So we have to match that. And if we go back, so they're all, centered roughly in this area. Obviously, if you give your algorithm input that is different than what it's trained on, it's going to produce junk values out. Yes?
You could pretty easily center it automatically before you run the algorithm.
Yes, you could. And that's one of the things we'll talk about, hey, improving. How can we go about improving this? But really, the key is, what are we going to use for our input data? Or what do we want to use our input data going forward? And then we collect our test data to match that. And we build our algorithm off of the data we expect to use in production. I think there's 60,000. I think there's 60,000 tests and 20,000, 60,000 training images and 20,000 test images, I believe is the number. So the overall accuracy of this is actually, I think, of this algorithm, I think was about 83%, which is actually pretty terrible. But it's because we did a lot of shortcuts where we define, well, we're going to round everything up to 1s. We're not going to use the density values and things like that. So if we did, one of the ones that always seems to fail is 0, I believe. Yeah, so that gives us an 8. Every single time it gives an 8. But most of the other ones are pretty good. And you can do some, there's some things, let's see, what do you have to do? With 6s you had to do kind of angled, I think. Yeah, or it comes out with a 5. So some of these are better than others. And you would look at the individual performance of each algorithm and say, why is this performance so low? And then determine ways, how can I improve this particular algorithm? So if 0 is always failing, well, maybe we need higher resolution values. Maybe we need to use density in some way. Obviously, we're using an exact thick border. Perhaps we use a way where it can get actual density values out of that ink library.
I might be anticipating what you'll say later, but I'd be interested in training this on my own handwriting. Did you explore that?
I did not, because you need a lot of data, and I didn't want to write out that many numbers. But yes, you absolutely could train it on your own handwriting.
What I was thinking, maybe initially train it on the MNIST data set, but then just learn online as you just correct it, say, no, that's a 6.
That's how voice recognition.
Yes.
Okay, Google. You have to say it 3 different times.
Yes, you would want to use, you wouldn't use this particular algorithm to do something like that. You would pick different algorithms to do that are more complicated. This is just a simple linear regression algorithm. It's one of the most basic ones, but as you can see, it still gives you decent results for demo purposes. And this, to put this together was only a couple hours to put the code together. So once you know how to implement it, now you can go back and look, all right, well, where am I failing at? What can I do better? Hey, my MNIST data set is only 28 by 28. Maybe there's a better data set out there that has 50 by 50 or something like that. So let's talk about ways to improve it. which we already kind of covered a little bit. But all right, so we already talked about utilizing gradients or density values. The MNIST data set has those values. We just ignored them, but you could use them. You could use a neural net. We use a simple logistics regression calculation that is literally, let's fit a line to this curve. Not really accurate. Outside the scope, but a neural net is basically allows you to say, we're going to design a algorithm that learns from another algorithm, essentially. And it just builds on itself. So you could have, let's just say we've got our original, all right, so let's just say we're trying to get 10 algorithms out, right? And we've got our input data. You could build 25 algorithms in the middle that learn from the data set, and then your 10 algorithms learn from those 25. And that's what a neural net does in essence. When you start talking about deep learning, that's when you start adding even more layers. So you could have, instead of just having your input, a hidden layer, and your output, you could have an input and 3 hidden layers that all learn from each other. And that's actually how, if you've seen, what is that app that, that takes pictures and turns them to artwork? Anybody know what I'm talking about? Huh? Prisma? Yes, Prisma. That's it. So what they did is they trained a neural network on like Picasso paintings and said, this is Picasso's style. And then what they did is they took those first layers and replaced them with your picture data. So then your picture came out as the algorithm interpreted it would be as if it was a Picasso painting. It was really interesting stuff, but that's how they did that. And they did that using deep learning. And then, so you train the deep learning model on your Picasso data set, and then you take out pieces of it and replace it with different data. And that's how they interpreted those pictures. There's really, there's a couple.
What was the name of it?
A Prisma, I think.
Prisma.
Yeah. Yeah, was it iOS and Android?
Yeah.
Okay, yeah. So, image centering. So obviously we didn't do any sort of image centering or cleaning up of our input data. When I drew it exactly where I knew it should be in order to get the exact information out. Higher resolution, where I talked about, yeah.
You mentioned deep learning as another deeper layer of neural net.
Yeah.
Would deep learning then, since it's not in your list, not be a method of improving the accuracy here?
Not with this algorithm. Deep learning doesn't make sense with the logistics regression algorithm that we used. Deep learning would be utilized on a neural net, not on a logistics regression algorithm. And we didn't really cover the differences because we're already almost out of time. Oh, I guess we got 12 minutes left. But it would take a lot more time to explain the differences and to diagram it out. I actually started doing a neural net to compare the two, and I realized we're not going to have enough time to talk about both. So. Yeah, I guess that was all the things I had on improving accuracy. What other questions do we have? We could try and download Prismat and show you. Or Prisma, is it Prisma? Yeah.
How'd you pick your alpha?
So that was actually, here it is, perfect. That's the function I use, that fmin-unc, actually does the calculation of alpha for you. You don't have to pick it. That was one of the shortcuts that I used. Yeah?
So I know it's outside of scope of what you were kind of showing, but like, would support vector machine be a better like approach than trying to like analyze each one of the individual output classifications?
Whether it's better, you'd have to actually just do it and see.
I'm just curious. I mean, I know you're illustrating.
It's another way of doing it. I don't know off the top of my head whether it would be a better way of doing it or not. All right, so I'm going to pull it up. All right, what should we take a picture of? Let's just take a picture of my water bottle. And let's turn this into servers. All right, how does this work? Level blending, there you go. So, again, it's just replacing the input data with a style neural net and saying, this is the output it would be. So, yeah?
Is there like a typical relative size of training data versus test data that you use? How much training?
So there's ways, you can plot what are called learning curves, which can kind of give you an idea if you need more data or not. There's not really a defined line. It really depends on what you're trying to learn. If you're trying to learn a really complex data set, the more data is definitely helpful. One of the things that's out there, and I don't have a picture of it, but there's a diagram between various different learning algorithms relative to data set size. And you can clearly see that while some algorithms are slightly better than others, the real key is the more data, the better off you are. So you're never going to go wrong with getting more data. The real key to figure out is it going to take me more time to collect this data than I would gain a benefit by doing something else with my algorithm, like improving the algorithm or something. So it becomes like a time trade-off. And there's curves you can kind of diagram to say, hey, it's likely that more data would improve or it's likely not. But there's no real set, you need 50,000 images or whatever.
I mean, like, suppose you have 1 million images. Is it standard to, like, take 80% of it?
Oh, yes. So yes. So the standard values, if you will, are to take 80% for a training data, and then you leave 20% as your test data. Or you can take 60% as your training data, and then you use 15% as what's called a cross-validation data set, and 15% as your test data. So what you do is you use your 60% to build your initial algorithm, and then you run that out. Then you run it, say, if you want to test alpha, for example, you would test alpha, say, 10 times against that training data, and you would measure it against your cross-validation data and pick the best alpha. Then you would run it using that alpha against your test data to say, this is the predicted output. We've got an 80% accuracy. Because again, if you're training your data on your training set, and then you're picking the best alpha off of your cross-validation set, and then you get your final accuracy percentage off of your test set. So again, you don't want to get your predicted accuracy off of any data you use to manipulate your algorithm. So those are the kind of general percentages you use. But obviously, you can do whatever you want, really. But yeah.
I really like how you presented this. You could have come up here and just done a math presentation and nobody would have followed it. So, props. I guess my question to you is, every time I look into machine learning, you do get inundated with math problems you don't understand. So how did you learn this stuff? And can you recommend any awesome books that give you these cool libraries and cheat sheets?
Books. No, I don't. So one of the courses I can recommend, it's on Coursera. There's a lot of math. However, you can kind of skip over the math and ignore it because there are a lot of pre-built libraries and functions out there that will do a lot of it for you. You do need to have a basic understanding of what the pieces are and how they relate, but you don't necessarily need to know the math. It's helpful, but yeah.
No, the course in Coursera was the Introduction to Machine Learning by Andrew Amy.
Yeah.
It's a Stanford class, right?
Yes. Yeah.
That's really good.
There's also always TensorFlow, which I'm using.
Yeah, so there's a TensorFlow demo, and I was going to use TensorFlow initially, but getting data out of TensorFlow isn't, I couldn't figure it out. That's why I switched to Octave. But yeah, there's some good TensorFlow demos. You really should have a basic I would suggest taking some basic course or reading a book or two on the basics before you try and start learning how those TensorFlow ones. You can get the TensorFlow ones working, but you won't really understand it without having a basic understanding of what the parts of machine learning algorithms are and how they relate to each other. So.
That Stanford class comes with a free book.
Does it? Oh, didn't know that. Yeah.
In your opinion, what would be harder to do, acquiring the data set or acquiring the algorithms?
The algorithms are easy. Acquiring the data set is probably the most difficult. And not just acquiring the data, but acquiring the correct data. So you need to have a clean data set that provides you with the input that you're going to expect in a production environment. So you can get data, but it might not be accurate. You might have to go through and manually change it and adapt it to meet your needs. The algorithms, there's so many resources out there that'll do the algorithms for you. I would say it's definitely harder to get the data and get the data in a good form. So that's why I used the MNIST data set, because it was out there. It's, huh?
What's the data set?
It's the MNIST data set. I'm trying to think what it's what the TensorFlow demo, if you just look up handwriting recognition TensorFlow, it's what they use. And their accuracy, I mean, their base accuracy is 93% using the TensorFlow stuff. And then there's ways you can get up way higher than that. So, yeah.
So an easy introduction for those who want to just get going, maybe look at Rapid Miner.
Rapid Miner?
Yeah,
I-
they have a free version. It's an easy way to get it. There's tons of like YouTube videos teaching you how to use various ones.
What is Rapid Miner?
It's a machine learning set of algorithms.
Oh, okay. So if you didn't hear Rapid Miner, I guess we'll.
That's a standard one.
Okay. Standard thing you can Google, I'm sure. So, any other questions? Yeah.
So you're gonna put a URL up for your-
Oh, yes, sorry. Yes, I did say that, didn't I? Come on. Where? Oh, duh. So this is it right here. Can I zoom in? No. Yeah, I know. There's a link. The slides, the octave code. Yes. That's my GitHub handle.
Like spray cheese?
Yeah, those little cans of cheese.
You're a scuba guy?
I do have my scuba license.
No,
Yeah.
I was just gonna mention there's a group in the Twin Cities called Mini Analytics, and they meet up like every few weeks, and they have,
What is it? Mini analytics?
yeah. And,
Like
they do
that? Ah. All right.
And they have like, test data from like some nonprofits here, and they have like contests.
There's some really interesting applications. There's an engineer who used TensorFlow to, his family had, I think it was a cucumber farm, and they were manually sorting cucumbers because it would take a long, like you could get a huge amount of value for good cucumbers versus bad ones. So he trained using a Raspberry Pi and a camera, he trained a machine learning algorithm that automatically sort these cucumbers into categories of quality. It was really quite interesting. And he did it, he had no machine learning expertise whatsoever, but he used TensorFlow and all sorts of free resources. But yeah. Any other questions? Cool.